Good afternoon, everyone. Welcome to a particularly toasty but nonetheless very welcoming session after lunch. My name is Jeffrey Wehner and I work for Duke Energy, and today's topic is avoiding catastrophes. And as I was preparing for this presentation this afternoon and looking at the credentials of my esteemed colleagues, I was very impressed with the brain power that's up on the stage. Each one, we've got doctors up here, and so half of me wants to really take a moment to talk about the value of education. I have 4 college degrees myself, but you know, the other half of me wants to say, 4 doctors and a lawyer walk into a conference. And I'm not sure what the punchline is, but I'm sure it's about to play out before you today. So, what we have is some very interesting items that occur, some fairly regularly, some very rarely. And what we want to do is try to harness the value out of this discussion. What you could very easily do walking away from the incidents that we're talking about today is say that these are the black swan events. These are things that very rarely, likely are never going to happen to me. And if that's what you take away, you failed, you should have been on the beach. My apologies. But what we want to do is to really consider not only what we're talking about here today, but really kind of push it into the realm of operational excellence. At Duke Energy, we like to say that when we talk about operational excellence, we talk about raising the discipline of our operations. That is to say, operational excellence is that level of discipline you're needing to operate event-free. Not error-free, because we're all humans and we make errors, but hopefully we have infrastructure in place to prevent those from becoming something more terrible. And one of the key aspects of operational excellence is always finding those opportunities for continuous improvement, being hungry for those examples where you can improve your operations, where you can raise the discipline. Sometimes those opportunities are very, very obvious, and sometimes they're very, very subtle. But finding that culture of excellence, that culture of hunger to look out and seek out those opportunities is extremely important. And from my perspective, you know, operational excellence isn't a metric, it isn't a goal, it's a culture, it's a way of thinking. So as we talk about, in some instances, tower failures, and in some instances, foundation failures, and in some instances, gearbox failures, let's think about how we would approach these at our different organizations. Let's think about the lessons learned. Let's think about thinking beyond the fix. So with that, I'm going to introduce our colleagues, and we'll just kind of go through their presentations one at a time, and we'll hold question and answer till the end. If you have the app, we'll be receiving questions through the app, and there's some directions there on the chart. But with that, I'm going to hand it over to John. John, who are you and why are you here?
Who am I and why am I here? Alrighty. Howdy, everybody. Ooh, okay, that projects, doesn't it? I'm John Hasler. I'm a senior scientist in material science and failure analysis at Intertek. I've worked in a variety of different industries, from aerospace, where I was working on liquid rocket motor, combustor, and injector design. I was basically a rocket proctologist. I have done structural, functional materials, magnetic materials, energy storage materials, worked at startups, large engineering service firms, and kind of bounced around, and now I'm in wind. They let me in the turbines. It's great. I like having a good time. I like any sort of field that has interesting people and interesting problems, and I found that that's led me to lead an interesting life. And I'm here to talk to you about the importance of failure analysis and root cause hazard analysis following hazard incidents. Let's see if we got, is that good? Okay, cool. Yeah, so this is going to be a pretty quick, simple, easy talk. Hopefully you all get something out of it. I had a great time working the job, so hopefully I can kind of transfer some of that enthusiasm and maybe a little bit of knowledge. We started out, we had some direct drive wind turbine trip incidents. We're going to talk about those, the immediate response to those. We're going to talk about how they attempted to solve the problem and remediate it. Then we did a failure analysis investigation. So you want to get ahead of your failures, you might want to renumber some of the bullet points. Then we'll talk about root cause and the lessons learned, and then I'll pass it off to my next colleague because they have way cooler slides than me. I've seen the receipts. They've got them. So direct drive wind turbines. We had an onshore wind generation site that had repeated trip of several direct drive wind turbines. The suspected cause was arcing of the turbines causing shutdown. There was a concern about this. They were getting some mixed signals from their SCADA system, and they opted to shut the units down rather than try to bypass it or override the trip. Even though the temperature sensors were saying everything is fine, they were getting some funny noise, and this was a great thing because the stator windings showed low resistance from coil to ground and from phase to phase, which meant that the insulation had been compromised. And when they opened up the stator to look at it, it was full of insulation residue and insulation material that had migrated out of the stator and was no longer performing its duty. Now, there were some issues with moisture on this site. Due to the design of the cooling system on the unit, any moisture in the ambient environment was being ingested into the turbine, and due to high ambient humidity and a lot of rain on site, they had standing water in the turbines. That was an issue that they were worried, when they would set the coils for layup that the moisture would set in there, and they were concerned that maybe it was a moisture problem. They tried baking them out, didn't really fix anything, didn't really change the polarization curves for their installation. And again, like I said, the temperatures didn't exceed the temperature rating of the insulation, so they were fairly confident they didn't have an overheating issue based on the ops data they were seeing. So they started to work the problem. Why is my insulation failing? And they got together with their OEM. OEM was very supportive of their operations on site. Of course, they were still in warranty, so some people have mixed experience with that. But we're talking about operational excellence. There was some really good stuff in here. They got together. They decided they're going to do some test rewinds in some of the units in the key areas where they were seeing melting. And they were going to replace the existing conductor with higher capacity current conductor and increase the amount of insulation so that the resistance from phase to phase within the motor was high enough to continue operation. There was no evidence of arcing shorts in any of the windings when they were taken apart, and so they weren't concerned about the loss of total insulation within the unit. They buttoned things up and began operating again. Of course, if that was where my slideshow ended, I'd be well under time. And so we know that did not solve the problem. In fact, less than 3 months after rewinding the units, they started seeing the same sort of trip signals, opened up the units, and found that the places where the rewind was performed had a much more aggressive quantity of insulation and melted degraded material, both in the individual coils and well as migrated out through the ferrite stack. So we can see detail here. The replacement windings, you'll look, are substantially degraded. Some of them, they have some dark material that was from cutting. We confirmed with the vendor that they were using a high-speed saw, and so that wasn't actually induced from the generator itself. It's good to know if they hadn't been keeping track of that information. It would have been better if they had used something a little gentler to cut it, but they were in a hurry to get it out and get it back to us, and so we try to remind people that how you extract your samples impacts how quick it takes to figure out what's going on with them. But we looked and we found that they had double wrapped with fiberglass, and the material within the fiberglass insulation had migrated substantially. And there was a concern from the operator that the supplier of the rewinding and the original equipment had not furnished appropriate insulation. It was supposed to be NEMA Class F insulation, which can go up to about 140 degrees C. And so we performed testing to verify the material content of the fresh rewound, because they were doing this on multiple units, they were able to pause the process and get us samples at different steps, both the replacement and the original hardware. Tested a wide variety of it using FTIR, DSC, TGA, visible spectroscopy techniques to validate the chemistry, bonding, degree of polymerization, and all of the resins and epoxies and fibers within were, of every section of everything we found, were determined to be consistent with a Class F insulation. Now, obviously, when this insulation was measured in the damaged state, it did not perform up to the task because it had been degraded. However, from the fresh, new insulation material that we had, we were able to discern that you cannot physically get resin migration below about 180 C. That was the first onset of melting observed across all of the materials. And so if you have liquid leaking out of the coil, you know that you're well above that 140 safe operating limit. And so, you know, the insulation damage on the factory and the repaired sections were the same, and the DSC analysis suggested that the stator temperatures were around 180 to 200 C, and that was what was causing the enamel to be degraded and migrate. So, you know, the ops person comes back and says, but I'm not measuring any temperatures above 120 C, right? So obviously they have a temperature signal. If you look at this diagram, this is a schematic of their direct drive nacelle. And the stator temperature thermocouple was right at the top of the unit. And we all know heat rises, so that seems like a pretty good place to put if you're only going to measure one spot, that seems like a pretty good place to put your thermocouple. However, it totally ignored the fact that the nacelle as a whole was not operating as one thermal volume. It was basically two thermal systems separated by the turbine deck, which basically isolated any heat transfer from the air volume below and above. The below volume being inaccessible also meant that when water accumulated, it stayed there for a while, could ingress into the coils and kind of dissolve partially some of the polymers and loosen them up and reduce their ability to withstand current. So what does this mean? Well, it means that we have a measurement, but it's in the wrong location. And when we looked at the damage map from all of the units, every single one of them, most of the damage was between the 8 o'clock and the 5 o'clock position on the stator. So pretty clearly everything below the turbine deck was getting heated up, and it didn't matter what the temperature above the turbine deck was. So that was a big clue that this wasn't a insulation degradation caused by current or induced by some electronic problem or manufacturing or rewinding problem, but that this damage was a thermal problem, which then suddenly made everything make sense, because initially these units had started to fail prematurely, sure, but we're talking about 5-6 years in the field from commissioning. When the repair happened, it was only in a few months. And well, why would that be? Well, when they did the repair, they increased the current carrying capacity of each coil in the damaged section, and then they doubled up on the insulation. And doubling up the insulation sounds great to prevent electrical faults, except for the fact that the electrical faults are being induced by heat generated in the conductors melting the insulation, which if you double up on the amount of insulation, you're much more likely to have heat stay in the conductor near the wire, where it's going to damage the insulation, melt things, and continue this cascading failure. So the stator insulation failure was driven primarily by thermal degradation, assisted by moisture ingress. We had localized elevated temperature degrading the enamel. There was a lot of turbulence on this site, and because of the way the direct drive works, the magnetic field is not uniform during operations, especially when there's a lot of non-uniform loading on the blades and speed changes. And turbulence being acted on it. Basically, magnetic slip compensates and allows the direct drive to move at different speeds. And when that slip occurs, you have hot spots that get generated. They're very hard to model. So post-repair, they failed a lot faster because they didn't mitigate any of the underlying issues. Suction of water in hurt. And so the result was they fixed the problem immediately, only for it to immediately fail again. The takeaways here are operating safely can prevent expensive catastrophic events, right? They did stop operating when they were getting this repeat error that could have turned into a fire. Even when everyone's working together, it's possible to hurt yourself a lot by not solving the problem before you understand it. And you want to examine your equipment, your operations, and environment while identifying and troubleshooting a failure. Otherwise, you'll miss the context that's telling you what the root cause is. Another takeaway, electrical insulators are typically good thermal insulators, which means if you have a heat problem, they're going to make it worse. Having a sensor does not mean that you're measuring what's important, so you need to think about sensors in context, and a holistic view of failure enables safer, more productive operations. And everybody coming together at the very end means that they managed to solve this problem, they redesigned the cooling system, and they're going to be operating for years to come. I haven't heard from them at all. It's been very bad for my bank account, but very good for the customers. Thank you.
Thank you, John. Very interesting. Very interesting. How many times have we thought that we knew what the problem was, we implemented a fix, and then the problem started happening more rapidly, right? It's a questioning attitude that's really, really important. So I want to continue on with this theme, and I'm going to welcome Kim. Kim, same question. Who are you and why are you here?
Thanks. Hi, I'm Kim Mortstock, and I'm a principal engineer at DNVGL. I've had a variety of roles over my 13 years there, but I'm currently in our O&M advisory services department in wind technology. So I will get started. First, I want to acknowledge my co-author, Sally Wright, in putting together this presentation about the unlikely but catastrophic event of turbine failures and turbine collapses. And I also want to acknowledge that 10 minutes isn't an exceptionally long time to go into details, so I do look forward to questions at the end of the session. So, what do you do when a turbine collapses? And in this talk, I'll be discussing how common or uncommon turbine collapses are, some of the causes, and really trying to provide some guidance for mitigating the risk, and essentially answering the questions, what do you do before this happens? I will start with the data that we were looking at. So we looked at publicly available data between 2013 and 2019, only in Europe and North America, where we thought we had the best set of statistics. And we also looked at turbines that were at least 1 megawatt at rating. The plot on the right is the blue shows the approximate number of turbines installed since 2000 over time, and the big orange numbers are the number of turbine collapses each year, so somewhere between 0 and 5 during those 7 years. So looking at that in an average sense, it's something like 3 collapses a year, or 1 every 38,000 turbines per year. These were spread across 5 major OEMs. There were a few of the 22 collapses that the OEM has not identified. And during this period and during this, in this region, there weren't fatalities involved, and there was also no impact on the public that we know of. And just to note that fire-related failures are not discussed here. It's a topic for an entirely different talk. So let's start with what are the causes of these collapses. We divided them into categories where it was known. It's about a third of cases we didn't have a cause that we were aware of or had access to. So any of these other categories could be broader. Controls I will talk about more in detail, and then the other ones I will basically mention in terms of how you would mitigate the risks. You can look through these later. There we go. So what do we mean when we say controls was a cause of turbine collapse? I will give a couple of brief examples. So in one example, a pitch system failed to pitch the blades, and so the rotor was not able to slow down, and instead it led to an overspeed, and the stress on the turbine tower caused it to collapse. And in another instance, sometimes is caused by a slow or relatively slow response to a very rapid change in environmental conditions. So for example, if the blade finds itself in a kind of deep stall condition and the turbine controls aren't able to rectify that situation fast enough, then the blade can strike the tower and the tower collapses. You can hear that in these examples, there's a couple of different aspects to the control systems. There is the software, the algorithm telling the turbine what to do and what takes priority. And then there's also the physical hardware, for example, a pitch motor. So the reliability of both of those components is critical. So let's talk a little bit about what you can do before the collapse and to mitigate your risk. So again, starting with controls, we have just heard a case for a root cause analysis. And in this case, we'd also recommend a thorough, independent, and timely root cause analysis. And that's true even if certainly if a turbine collapses on your site, but also if it's a similar technology elsewhere in the world, then you're asking the OEM about that root cause analysis. And then if you know that this is caused by the control system, our strongest advice here is to get your control system updated promptly. And that does require a relationship with the OEM, so it is more of a challenge for turbines that are no longer supported by OEMs. And also just raising a question here, as turbine controls become more and more complex, so they're already regulating turbine performance, they're being used for loads management, and they're also involved in the safety chain, are the IEC standards to which turbines are certified evolving as rapidly as the changes in turbine control systems? I think it's an interesting question to discuss. So blades, you have heard at least one mechanism for collapse would be if a blade strikes a tower, but there are other potential mechanisms. So for example, a blade had been repaired, but it subsequently failed. It did not strike the tower, but the turbine wasn't able to recover from the imbalance that was caused by the sudden blade failure, and that tower also collapsed. My colleagues found, they reported a few years ago that about half of blade failures were caused by a manufacturing defect. So we are really recommending that you understand the quality of your blades right from the very beginning. So visiting the factory if that's possible. And then throughout the life cycle of the blade, following through with inspections and documenting and recording repairs so you can really understand the history of the blades in your fleet. We will hear more about foundations, and I think see this image again later. So I'll only note here that we advise storing data such as tower vibration data historically so that you can look for trends later to better assess the health of your tower and foundations. With construction, I will only note that, as production tax credit deadlines near, it can be more challenging, as we know, to maintain operational excellence, to maintain quality and safety measures. And we certainly know that many folks in the industry are doing that. Just want to emphasize its criticality for mitigating the risk of disasters such as the ones we're talking about. Now, extreme winds also occasionally cause turbine collapses. There's a few things you can do in the development phase or when you're setting up a wind farm, but in the end it may come down to the insurance terms if an extreme wind event hits your site. So in that case, we really recommend understanding the terms, understanding what your risk exposure is. For example, if force majeure and if lightning is not covered, what will you do in that situation, kind of understanding your risk there. And being aware that if a turbine does collapse, it can take more than a year to be replaced. So evaluating that in your business plan. So finally, If we have one, well, we have a couple of major takeaways here, right? So we're certainly advocating for operational excellence, following best practices at all stages, from the construction right through operations life cycle of the wind farm. And we also strongly urge people to understand any updates to the control system and to implement those promptly. We really just can't say strongly enough how much we advocate sharing of data across the industry so that we can learn from each other's issues. And finally, the images that I've showed in this presentation thus far can be kind of dramatic and can be used to scare the public. And so we want to say that we showed here through statistics, the risk of turbine collapse is there, but it's relatively rare. And there have been no known impacts to the public, so the risk to the public is very small. And that we as an industry are kind of sharing that relevant information and also sharing that we're doing all that we can to mitigate risks of disasters. So I'll just briefly acknowledge my sources, and also I'll be looking forward to questions after.
Thank you, Kim. Definitely appreciate kind of the insight. This is what we're here about, sharing information, really getting the lessons learned across the industry. I want to do a plug again for if you have any questions, use the app. We'll be fielding those. But now, last but not least, I'd like to invite Dilip to come up and talk to us.
Good afternoon. How's everybody today? I want to first thank AWEA and the panel for this session and for inviting me to be part of it. I want to especially thank them for the title, Avoiding Catastrophes. Did that catch your attention? You guys awake out there? And see, I was expecting a subtext under that, like something like how to start an offshore account or how to file your tax return, Just checking, making sure the mic is working, that's all. So a little bit about me. I'm a structural engineer for 37 years. I actually started in aerospace. Used to design planes, and I've been working in the wind energy industry now for more than 20 years. Towers and foundations is my business. We've worked on all of your projects. You just don't know who we are because we're underground. We're underneath everything, but you've worked with either one of the companies that I've worked with, which is Patrick and Henderson, or some of the other ones. We're a very small number, but we're out there. So my topic is to quickly give you an overview. Here's a scary thought. Everything that this industry does, everything that you do, sits on something that we designed. Think about that for a second. The whole thing, the whole power plant, the whole tower, it's all sitting on something that comes from the smallest companies and the smallest entities that are in this industry. And it is probably one of the least talked about and most secretive, I guess is the right word, because none of my clients want to know or talk about or have their product exposed that they have a problem with a foundation or a tower because it's so detrimental. So I am under multiple confidentiality agreements. I was going to bring a video to show you some actual tower collapses, but I could not edit out the name of the turbine on them. And so that's not good business, to show something happens, but it does happen. The different types of foundations that I've worked with, the common ones, the spread footing, the pile cap with concrete piles, pile cap with micropiles or anchors, gravity type, and the P&H. I'm sure you're familiar with all of them. And the bottom line is this, that the choice between the different foundations boils down to one critical factor. Would anyone care to take a guess? Money. Because why spend $400,000 on a foundation if you can do it for $100,000? And also the site conditions. So being in this industry since the year 2000 and seeing how things have progressed, when I started in about 2000, 1999, roughly 20 years ago, I started with 660 kW turbines on 40-meter towers, and now I'm working with, holy Toledo, 5-megawatt turbines on 120-meter towers, and these things are huge. They're huge, and the foundations, nobody wants to make them larger. They want them to get smaller, so things have gotten even more competitive. So just to give you an order of magnitude, a 5-megawatt turbine with the rotor, how much do you think it weighs? Roughly, depending, of course, on the manufacturer and everything, but nobody wants to admit what their weights are. That's all confidential, right? So I'm not mentioning any names, but they're between, the light weights are around 400,000 pounds and the heavy weights up to 750,000 pounds. What does that mean? Well, a Boeing 747 empty is 400,000 pounds. A Boeing 747 full is 1 million pounds. So it's something like a jetliner that's sitting up there, 100 meters up in the sky. And it all rests on that. Now this sketch, the reason I put this in here is to give you an order of magnitude of the scale. This drawing is to scale. So you can see that little thing down there at the bottom. That's what I do. And that's where you have to pay attention. The other important thing to keep in mind, and this is pretty much true across the board, I don't think there's any exceptions to this rule. I haven't found one anyway. If there is, I'm sure someone will correct me. There is no turbine manufacturer out there, and if there is, please speak up. There is no turbine manufacturer out there today that will warranty or guarantee the foundation. They only will warranty or guarantee up to the tower, and the foundation is the contractor's responsibility or the designer's responsibility. And that's very important to understand because all of the warranties and guarantees you get stop where that flange meets the foundation. And so that's why it's apparent, it's very important to pay attention to it. So my colleague earlier talked about issues with the nacelle, but foundation issues will shorten the service life, and they can, for lack of a better term, they can kill a project if they're not designed properly. And so what do you look for? Well, the biggest clues, and first thing is to remember, I hope if anything you get out of this presentation today is to at least look, because most people don't even want to look. But cracks and tilt and fatigue failure and loss of rotational stiffness. So what the tower designers have done is that they have allowed, well, so here are the scare photos. These are the scary photos, right? So no names, right? No, everything is just somebody's project, so we don't want foundation failures. They're rare. They do happen. This one is available. I downloaded this from the internet. But before they actually reach that point, just even a little bit of tilt can render your tower dysfunctional. And that's not technically a catastrophe, but if a tower is not able to function and is not able to generate power, that's a financial catastrophe. And then, if it gets worse, it gets worse. So again, as I was talking about, the growth of the industry is unbelievable. Things are getting bigger, larger, heavier, more demanding. It's gotten a lot more sophisticated. And as I said earlier, we've gone, from little 6.6 kWs, where now we've got 5-megawatt turbines, and they're getting larger. The rotor diameters, 130 diameter rotors, these things are huge. So that means you have to pay more attention to what's underground, which nobody warranties, nobody guarantees. And so you as a project developer, project O&M manager need to pay attention to those things. So as I said earlier, everything is supported on the foundation. So what do you look for? I'm just going to give you a couple quick pointers of clues that you should be paying attention to that you can do on your own. You don't have to hire anybody. You don't have to spend a lot of money to do this, but before a foundation is going to actually show real signs of distress, it's going to give you clues. It's going to tell you that it's sick and that it needs attention. And they're very simple clues. The first one is any amount of rotation. And when we're talking about rotation, we are now talking about down to definitely the 10th of a degree or possibly even the 100th of a degree of rotation, which you can't visually see, but you can measure using some very basic instruments without having to hire anybody. And if you see, because the rotational demand on the foundation is very, very tight. Because remember, I told you earlier, the tower designer and everybody above the flange line, they don't take responsibility for the foundation. So what they do is they dump all those requirements on us. And so we have to make that very rigid. So the first thing is rotation. And these are just some sample details from various projects, not any specific project. And here's the real equation. A very small amount of rotation is magnified up at the top with a tower tilt. And so that foundation being very important to measure that rotation and to measure your tower deflections on a regular basis when they're obviously not operating or on shutdown mode, so that you can see them in their true vertical or close to vertical, because there are limits on what that range is. Those limits vary from turbine manufacturer to turbine, from Vestas to Gamesa. They all have different ranges, but they all fall within a bandwidth. And all of the turbine manufacturers have, and this is all highly confidential to each turbine manufacturer, so I won't mention any names or what they specifically have. But for your specific project, there will be a range, and that range is good, bad, and the ugly. Good is okay, of course. Bad, well, you can still operate, and ugly is, of course, ugly. So you've got to pay attention to that. And again, different kinds of foundations require different kinds of observations, but everything you're looking for is going to be found at the base. And deflection, and the other one is cracking. We as civil engineers design all of our foundations to crack first before they fail. So cracking, even though it's ugly, is a signal that something worse is about to happen. We do the same thing with buildings too. We want them to crack first before they fail. And you understand why? Because we want you to get out before it fails. I mean, we don't like the building to collapse, but we don't want dead people is not a good thing to have on a resume. So we want you out of there. So we actually design it to crack. It's actually meant to crack first. And so these are signs, again, from various projects that I've worked on. I've been doing forensic work for 20 years for insurance companies, for owners. So I have a lot of these slides. And so it brings me to the another end of our business, which is repower, and everybody's really big on repower, and repower is great, provided that your basic structure that's carrying all that stuff up there, everything up can be replaced, even a tower can be replaced. It's very hard to replace a foundation. You can retrofit one, but the issue of repower now comes into what is the actual service life of that foundation. You're getting into fatigue issues. So just pay attention to those things. That's all I'm saying. That's really my only mission here, is to let you know who we are and what we do, because you probably never met one of us or know what we do. So what are the signs? Here are your rules of thumb. Deflection, deflection, deflection. Did I say deflection? Yes. If it moves, pay attention. Don't just assume that it's flexing. It's not a yoga, okay? If it's moving, it's not good, right? It shouldn't move at all, but it's going to move. Cracking, any kind of cracking, pay attention. Rotational movement, not good. Did I say deflection? Yes. And cracking, did I say cracking? And I will close with one on the spirit of our moderator. Since he started the joke, I'll finish the joke. An engineer, a lawyer, and a scientist were standing in line to get into heaven. But it was a little busy that day. And St. Peter said, you have to ask a question that God does not know the answer to. So the first person was the lawyer. And he said, was my appeal granted? And he said, no, go to the back of the line. Okay, forget about that. Then came the scientist who said, does God exist? He said, of course I do. Go to the back of the line. And then the engineer came up, he whispered his question, and St. Peter said, oh, we don't know the answer to that. And he gets into heaven, and the other two said, what did you ask him? He said, I just asked him when my kids were going to leave the house. Thank you.
So, does this work? Is this on? Hello? Hello? There we go. All right, so looking forward to having some questions from the audience. There's also questions within the slide deck itself or within the PowerPoint. And first off, are there any questions before I get into some of my own? With that, I got a question for Kim. What sort of age in your data set, what sort of age in the towers were out there?
Sure. So we only knew the age of about 80% of the tower collapses that we saw, and they were anywhere between 0, like less than a year, to 15 years. But the concentration really was between 0 and 4 years old. And we would say that some of the controls-related failures did tend to happen earlier in project life.
And you say that what sort of OEMs, if this is public information, can you give us a sign of what the OEMs were?
Sure, I did mention that it was across 5 major OEMs that we know of. And I don't see any reason to throw any OEMs under the bus. So, it's certainly, you can look up the news articles if you like. I think the one interesting thing that we saw in the data, again, for turbine types that we knew what they were, there were a few that were unknown, but many of the collapses did occur in machines that had AC electric pitch. So that is a correlation, not a causation, but we thought that was kind of an interesting aspect.
Thank you for that. So, John, your presentation was very interesting to me. As I look, I was just questioning, and I can see myself in that situation where it's not even on. All right, can you hear me? Is yours working? There we go. So I put myself in that situation where we think we know what the fix is and we put it online and it seems to be working for a while, and then all of a sudden it accelerates. And when I'm thinking about, concepts of operational excellence, one of the things you really want to reward is that questioning attitude, right? Rewarding people for trying to think beyond the fix. But I wonder in that particular instance, how long did it take to figure out that the thermocouple was reading something that wasn't apparent to the cause? And how did you get to that solution?
So when we had been brought on, it was well after they started seeing the string of second failures. And we very quickly, within a few weeks, kind of came up with a lot of this based on just looking at the design and really bringing together the operations data and the inspection data. At Intertek, in my asset integrity management division, we deal with a wide variety of data types, and we have a lot of experts that are working in an interdisciplinary way rather than a multidisciplinary way. And so we were very quickly able to realize that this was very likely not related to a fault in the equipment or the manufacturer. And then it was just down to running as many quick tests as we could to back that up with facts. Because everybody was kind of pushing back and pointing fingers at everyone else, which was really that's what resulted in a third party being involved. A lot of times, we say get a third party involved early. It's because you're going to spend a lot less time fighting with each other because you'll all just have someone that you can look at and be like, what's going on? Whereas if everybody's collecting their own data, it's chaos. And so I think the chaos is really what slowed things down when the easy fix didn't quite do it. And so if they had done an RCA to begin with, we may not have even ever gotten a call, which, I'm all about putting myself out of business, it seems like.
And that's a great point. RCAs are really a good way to focus on the solution rather than something else that could metastasize. So, Dilip, a question for you. Very interesting presentation. And I guess I knew this in the back of my head, but you really put it out there, that the risk of those things are really on us, the owners. And maybe it's potentially one of the most unappreciated risks that is out there. What do you recommend is, you're sitting in the audience out there, you might not have considered this before. What would you recommend? Would you recommend an inspection program? Are there things you think we should look at first? Should we hire you? Should we hire somebody else? What would you recommend?
Thank you so much. Well, of course, hire me. No, I'm just kidding. So the first thing is monitoring, and that's why I gave you some very simple rules of thumb, which are not expensive, and just paying attention, monitoring, doing physical inspections for sure. I will share with you just one very brief anecdotal story without mentioning the project. for the turbine manufacturer, which I worked on in the last year. I had a project which was designed by the developer's contractor's foundation engineer, a major firm. They designed this foundation, they built the foundation, and the turbine manufacturer had some concerns because right away in the first storm, there were cracks, deflection, and so on. So the turbine manufacturer, remember the turbine manufacturer, my client, does not have responsibility for the foundation, hired my firm to do a full evaluation of the design, which I did, and I pointed out a lot of problems. They took my report and they put it in their safe, and they did not share it with that owner, and they dealt with the discussions and basically said, well, we'll pull this report out when we need to. So it is a highly, highly confidential based industry. And so for you as an owner, or even a turbine manufacturer, again, monitoring, and then of course, when you need it, bring in an expert to actually take a look at it, because again, the signals, first of all, the signals will be there for sure, but that's the best you can do. But it is a situation where even if you're a developer, the turbine manufacturer that sold you everything may already have that information, but they won't tell you because they don't want to get into a legal situation, and we've worked on that circumstance.
Okay, that's terrifying. Thank you for that.
Sorry. True story, but we worked with, so I have worked with all the major ones, okay? So no names, it's all highly common, but yes, that is correct.
All right, so I want to drill into that some more. So you say any sort of cracking. And again, I'm a chemical engineer and I'm an attorney, I'm an executive, so I don't know what the hell I'm talking about up here. But is it any cracking, literally any cracking?
Well, first of all, concrete will crack, period. So you will have what's called shrinkage cracking, which is normal. But the reason I say any and all cracking is to just raise your awareness, because you don't know the difference between a shrinkage crack and a flexural crack and a structural crack, and you don't know what the tolerances are. So rather than me getting into another discussion of a good crack versus a bad crack, which is probably a 3-day conference by itself, and I know you're all really excited here. I can see
So
that.
you're talking about a conference about crack.
I'm attending.
Sorry. Sorry?
I said I'm attending.
Yeah, no, you don't want to attend that conference. No, it's.
No,
We have a whole. Did you know there's a whole organization called American Concrete Institute? They have a whole seminar on cracking, and that's why that's the one where I tell the joke about the crackhead. No, it's, never mind.
Very nice.
But so the point is pay attention. I'm just trying to raise you to pay attention, because you're all brilliant people. I know that. I'm the low-tech guy in the audience here, You're all brilliant people, and you're all focused on the gizmo up there. Forgive me for my, simplicity. But the gizmo and all the whatchamacallit with the gobbledygook is sitting on my stuff. So just pay attention, that's all, And then when you need it, you need to investigate it.
So it sounds like it would be a good time for me to go and make sure that we've got good pictures of our bases, and we're identifying any issues and really having a video record of it so we can reference it in the future.
Yes, and then really simple stuff like, again, not trying to get too technical, but an inclinometer, which is like a, $50 piece of equipment. You can put that on your foundation and just check it from time to time. Simple stuff. I don't like to advise people to spend a lot of money until they have to, because it's not necessary. Inclinometer, or you can do really sophisticated tool, right? Take your business card. This is really sophisticated. You put it on the crack, you put a pencil on it, and you tape it. And if it moves, bingo, you have a problem. So that doesn't cost you much.
Very cool. Thank you. So Kim, in one of your slides, you identified, again, public information, that it appeared to be approximately a third of the faults didn't have an understanding as to why it happened. Now, certainly that could have been a result of just not having the data out there publicly available, but I think you also identified that it just wasn't defined. So I guess when I looked at that, I was surprised. Is that an indication that perhaps, the concept and the culture of operational excellence is just not as mature as it needs to be in this business, or is it something else?
Well, I think there's kind of two ways to go with that. One is, you're right, it's publicly available information. So in some cases, it's a little report that says wind turbine fell over somewhere in Germany, and I don't even know what wind farm that was because there's a lot of wind turbines in Germany. But in other cases, we maybe did know more about the wind farm and the manufacturer and the owner and all of those things. But yeah, exactly. I think where we're going with this is that there's not a very good way to share information across the industry, and that information, doesn't get out. It's not publicized, and because of that, it's kind of who you know and what you hear, and coming to conferences like this. Certainly, we have a lot of room to improve, to share best practices, and to share lessons learned.
Yeah, thank you for that. I think, AWEA has a role to play in this. Really, together, we're stronger as an industry if we share information. And sometimes there's a challenge and a reluctance to share that information. But here's a good example where we might get some insights that might directly impact me. And I guess, as we're wrapping up here, if anybody has any questions, again, nobody has any questions. So let me just ask a question myself. And let me play devil's advocate. In your slide, we have 1 tower per 38,000. I mean, that seems like a very small fractional point. And there are people that I've seen, people in articles say that we're probably over-designing these towers because that failure rate is so very small. But yet, here we are talking about it. And I think what's fascinating in your recommendations, you have a bunch of recommendations that really we should be doing anyway, right? We should be updating our control parameters. We should have relationships with, the appropriate partners. And we do these things because it's good procedures. And I don't know if this is a question or a comment or if I'm just pontificating here, but having this overall cultural of excellence, making sure that we have policies that we're following, procedures that we're following, that we're identifying those opportunities. The issue you might solve might be avoiding a tower failure, or it might be something else. But ultimately, the end result is avoiding all the catastrophes that were happening. And so I think if there's no more questions, I'd like to thank my panelists and the brain power that's certainly on that side of the stage, and appreciate everyone for spending their time with us this afternoon. Thank you.